All right, so simplifying cube roots is similar to simplifying square roots, but instead of finding perfect squares, we're going to find perfect cubes. We're going to find our 3 of a kinds. So we can expand these. I don't usually expand them because it gets really long. But I'll do this very first one that way, just so you have the idea of it, and then we're going to try to make it a little simpler. So if I expand everything under the radical, 16 is 2 times 2 times 2 times 2. And then I would have 5 x's. You'll see really quickly why I don't do this usually. 1, 2, 3, 4, 5. And we have 13 y's. So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you've already discovered why this is not the preferred method. Now I'm going to look for my 3 of a kinds. Okay? So I see I have 3 2's, and I've got 3 x's, and I've got y's 1, 2, 3, 4 times. So I get to pull all those out. I'm going to pull out a 2 and an x and a y to the 4th. Underneath my cube root, I have a 2 left, I have x squared left, and I have a y left. And so that's my final answer. Be really careful that you are including the index in your final answer. If you don't include the index, you're saying square root, and that would not be correct. Are we okay with that part? Okay? So I'm going to work towards not expanding. We're going to try to see if we can figure out how many 3 of a kinds we have without writing all that out. I might still do this with the, I might still expand my constant value, but the rest of it's kind of a bit much. So I still have this 2ab squared I'm going to leave on the outside. I'm going to look at this negative 54. Okay, this negative, I'm not going to have an imaginary number. I can think of the negative as negative 1 times negative 1 times negative 1, right? If I multiply that all together, what's negative 1 times negative 1 times negative 1? Negative 1. All right, 54 we know is 9 times 6. So there's 9 and there's 6. All right, and then I'm going to deal with the letters in just a minute, the variables. So I'm going to pull out a negative 1 and I'm going to pull out a 3. So I get to pull out a negative 3. And so I'm going to multiply that negative 3 by the 2. Right, those guys are going to go together. Let's look at this a to the 8th. So imagine I've got 8 a's. So if I think about, I've got 8 a's. So how many sets of 3 do I have? 2. I can say, okay, 8 divided by 3 is 2. So I'm going to pull out 2 a's. That's basically 6 a's underneath the radical. How many would be left over? 2. So I'm still going to have a squared underneath the radical. And then let's look at the b. So I'm going to have 4 sets of b's that come out. So basically I'm going to say 12 divided by 3 is 4. So I'm going to multiply this by b to the 4th. Will there be any left over underneath the radical? No. All right, so outside the radical, I have 2 times negative 3, which is negative 6. I have a times a squared, which is a to the 3rd power. I have b squared times b to the 4th, which is b to the 6th power. And underneath the cube root, I have 2a squared. So we're going to do more of this tomorrow. I'm going to come back and fill these out in just a minute. So if I have like the 5th root of a to the 7th power. All right, if I have the 5th root of a to the 7th power. So basically, I can write this. We're going to do fractional exponents tomorrow. This means a to the 7th, and I'm really dividing that exponent by the index. So I'm going to take this little fraction and I'm going to rewrite it as a mixed number. So how many times does 5 go into 7? 1 time, with how many left over? 2. All right. So this whole number is what I'm going to pull outside of the radical. And then what's underneath is going to be this exponent there. So that's where we're working towards. We're going to do this a lot more tomorrow. If you don't see this today, it's not a problem. But that's why I never expand. If I go back here, if I think about this a to the 8th, so a to the 8 divided by 3, 3 goes into 8 2 times with 2/3 left over. So this 2 here is the same as this 2 here. And then this little 2 exponent here is where I got this little 2 exponent there. If I took 12 divided by 3, I got 4, and there was no remainder. So if I say b to the 12 divided by 3, it's b to the 4th. So the whole number comes in front of the radical. The fraction stays underneath the radical. Okay. Also, just like square roots, we get to combine them when we have like terms. Okay, so right off the bat, neither of these appear to be like terms, but can we simplify them to make them like terms? All right, so if I look at this first one, 16 is 2 times 2 times 2 times 2 times, I'm going to just expand it for just a minute. Am I going to be able to pull out any y's? No, because I need 3 of a kind. But I can pull out a 2. So I end up with 2 cube roots of 2y squared. So that's what my first term simplifies to. If I look at the second term, bless you. 54 we said was 9 times 6, so 3 times 3 times 3 times 2 times y times y. So I have 3 of a kind with my 3's, which I can pull out, and that's all. And I'm also left with 2y squared. So now because the radicals are like terms there, I can add the coefficients. So 2 plus 3 is 5. And I have cube roots of 2y squared. You guys want to try the next one? Okay. Also, like square roots, we can divide under the cube root. So this is only going to be true if my numerator is a cube root and my denominator is a cube root. You can put them together, and we can reduce first. So Caitlin, I think this is more along the lines of where when you divide bases, you subtract exponents, where you were going. So here, m to the 10th divided by m squared is m to the 8th power. N to the 7th divided by n to the 1st power is n to the 6th power. And now I start looking for my 3 of a kinds. Yes, sir. All right, so if I have, how many pairs, how many 3 of a kinds, how many m's will I have if there's 8? I get to pull out 2 of them. And what's left underneath that cube root? 2. And then what about the n's? How many can I pull out? Is there anything left underneath? So then I'm done. Okay, so number 6 here. I have a radical in the denominator. I can't leave a radical in the denominator. I'm going to rewrite this a second. I'm going to write this as the cube root of 5 times 5. What else would I need in the denominator in order to get rid of that radical? I need another cube root of 5. So I'm not going to just, like I did with square roots, I'm not going to say this. I'm not going to do that. That doesn't help me. That doesn't clear the denominator. What's going to clear the denominator is just one more radical 5. Okay, so let me erase this. This isn't going to help me. But just one more radical 5 will clear the denominator. So in the numerator, I'm going to have 4 times the cube root of 5 And in the denominator then, I'm going to have 5 times 5 times 5, which lets me pull out that 5. So what's different about these two is they have a different index. So it's not a cube root, it's a 4th root and a 5th root. But that's okay. All this means is 4 of a kind or 5 of a kind. So let's break this down. So I have the -2, I have the 4th root. So if I wrote 48 prime factorization, I have 2 times 24, which is 2 times 12. 12 is 2 times 6. 6 is 2 times 3. All right. And I'm just going to, for this first time, I'm just going to do this. And then the next time I'll use my fractions. So I've got 6 p's, 1, 2, 3, 4, 5, 6. And I've got 11, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so now I'm looking for, my index says 4 of a kind. So I have 4 of those. 1, 2, 3, 4. I have 4 of those. 1, 2, 3. I have 4 of those. 1, 2, 3. I have 4 of those. So I have still the -2 that I started with. And I'm going to pull out a 2. And I'm going to pull out 1 p. And I'm going to pull out 2 r's. And underneath that 4th root, I'm left with a 3 and a p squared and an r to the 3rd. So the last thing I need to do is just clean that up. All right, not too bad. So now let's look at the 5th root. So it's the same value. I'm just going to change colors here. So I still have the -2. Am I going to pull anything out of this 48? Do you see 5 of a kind? Nope. So underneath that radical, that 48 is going to stay. Now, p's, I do have 5 of them. So I'll pull 1 out, and that'll leave 1 underneath. Out of the 11 r's, let's see, there's 1 and 2. So r squared with just 1 left over underneath the radical.